Hello and welcome everybody. As promised, I am back with the second of 3 videos for the Chapter 4 AP Chem PowerPoint notes. So today we are going to talk about acids and bases, strong acids, weak acids, neutralization reactions, redox reactions, and then we'll probably make it about halfway through here. We'll end this video, start with the final video, and that should wrap it up for the entire Chapter 4 PowerPoint. So happy to have you guys here. We left off with writing molecular, ionic, and net ionic equations. So let's jump right in to acids and bases. And as always, I may have disappeared, but I'm still in that upper corner right over here. I will just find where we're supposed to be. I will bring up this, and hey, looky right there. Gotta make myself a little smaller here. Hey, there we go. Put myself right there, and away we go. So acids and bases. So acids are usually anything that would, when dissolved in water, would dissociate into the hydrogen cation and the anion associated with the acid. So hydrochloric acid, hydro leading with a hydrogen, chloric with the chloride ion, you would have the hydrogen and the chloride ion dissociating. And the act of having a hydrogen ion go off in solution is what makes it an acid. Well, that definition didn't hold forever because along down the road, we had another chemist who came up with a more encompassing definition. So the first definition was done by Arrhenius, and an Arrhenius acid, named after himself, an Arrhenius acid would be an acid that increases the concentration of H plus ions or hydrogen ions in solution when dissolved in water. Now, how do you increase H plus ions? Well, you increase H plus ions by having them dissolve. So if I were to take some water, pour some hydrochloric acid into it, when that hydrochloric dissolves, the H plus ion concentration now in the solution will increase because it's receiving more from the acid. That's what we mean when we talk about an Arrhenius acid. We look at the hydrochloric, we look at nitric, we see the lone nitrogen located. Let me see if I can get a annotate. I want to spotlight there. Boom, we see this lone hydrogen right here. That's going to dissociate. With sulfuric, we see there are actually 2 hydrogens, one over here and one over here. Those would dissociate. And with acetic, we see there's 1, 2, 3, and 4 hydrogens that would dissociate. It doesn't necessarily mean that acetic acid is stronger than hydrochloric or nitric or sulfuric. This is just a number of hydrogens that are dissociating. Now, people started to realize, well, hey, you know, there are some compounds that do share acidic properties, but that may not outright look like they're donating hydrogen ions. So the more and more research that was done opened up the door to classify more compounds as acids, but they didn't fall underneath the Arrhenius, the original definition of being a hydrogen, increasing the hydrogen ion concentration. Instead, we now have an additional, not a new, well, I guess it is new, but it doesn't take away the Arrhenius definition. We still have that. We now have an additional definition known as the Bronsted and Lowry definition, Bronsted-Lowry definition of an acid. And this categorizes any substance as being an acid if it is a proton donor. A proton donor. We're going to get into exactly what it means to be a proton donor. All right. So acids, there are only 7 strong acids out there: hydrochloric, hydrobromic, hydroiodic. We look at our periodic table up there. We see chloric, bromic, and iodic are all halogens, right? Nitric, sulfuric, chloric from the chlorate ion, excuse me, and perchloric from the perchlorate ion. Okay, those are our 7 strong acids. Notice they all have an H in there. They would all increase the hydrogen ion concentration when dissolved in water. Our bases, well, we have the Arrhenius base, which in this case, an acid would increase the hydrogen ion concentration. Now, a base is categorized by having an OH, sodium hydroxide, calcium hydroxide, magnesium hydroxide. So an Arrhenius definition of a base would be any substance that increases the OH, the hydroxide ion concentration in water. Whereas a Bronsted-Lowry base would be something that now accepts protons. A Bronsted-Lowry acid was something that would donate a proton. A Bronsted-Lowry base is now something that accepts a proton. Notice when we talk about litmus tests, acid always turns litmus paper red. Base always turns litmus paper blue. How can you remember that? Base blue, BB, right? Base turns litmus paper blue, red litmus paper blue. Acid turns blue litmus paper red. Just like we had 7 strong acids, hydrochloric, hydroiodic, hydrobromic, so on and so on, we have some strong bases. These are a little bit more all-encompassing. Strong bases are soluble in metal salts of the hydroxide ion. So we have any alkali metal. If we look at our periodic table, when we're talking about alkali, we're talking about lithium, sodium, potassium, rubidium, cesium, francium. So lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, rubidium hydroxide. All of these form strong bases or strong bases. Fun fact, hydrogen is also in the alkali metal family. And if you put a hydroxide with a hydrogen, you get HOH, which you know to be water H2O. H2O can also act as a base because it will accept a hydrogen ion. Calcium, strontium, barium, those are all your alkali, those are your alkaline earth metals. Those are also calcium hydroxide, strontium hydroxide, and barium hydroxide, all examples of strong bases as well. So how do we tell if something is strong or weak? Well, strong acids completely dissociate in water. They will 100% break apart. If I put in 10 milliliters of hydrochloric, then those 10 milliliters will all break apart. If I put in 10 milliliters of now base, calcium hydroxide, those 10 milliliters will break apart. Strong bases will also dissociate into metal cations and hydroxide anions in water. Weak bases, just like weak acids, will only partially dissociate. Only a small percentage or a certain percentage will break apart in water, which means if we have a weak acid, it is by definition a weak acid because part of it will remain as the acid in water. Not all of it will break apart. Okay. Your strong acids again, hydrochloric, hydrobromic, iodic, chloric, perchloric, nitric, and sulfuric. With your strong bases, we're looking at the group 1, the alkali metals, and group 2, calcium, strontium, and barium. So acid and base reaction. So first off, let's just take a quick look here at what we're talking about when we talk about strong acids and weak acids. And for that, we're just gonna pause this for 1 second. All right, everybody. So I think this shows a nice example of the difference between a strong and weak acid and base. If we take a look at this, we see here that we have a strong acid, it's hydrochloric acid. And when we dissolve that strong acid in water, it will completely break apart. It will dissociate as it has done right there. Now, the difference between a strong acid and a weak acid is that on this side, the strong acid, notice none of them are still bonded together. All the hydrogen ions have disassociated, making it a strong acid, 100%. And they are now floating around by their lonesome, and they are increasing the hydrogen ion concentration. Looking over now here, this would be considered our weak acid. The reason it's called our weak acid is because only a percentage of the acid has disassociated. We do see some hydrogen ions. Here's one, here's another floating around, and they're anions as well. But only some of them have disassociated. The ones that are being circled now are still in the acid, the hydrogen anion pair. So notice there are still some that are in the acid form, but also some that are disassociated. In a strong acid, everything disassociates 100%. In a weak not 100%. Less than 100% disassociates. The closer you get to 100%, the stronger the acid is. The closer you get to 0%, the weaker the acid is. So just a little visual there on the difference between a strong and weak acid. All right, everybody. So we are going to take a quick pause from the video because I want to dive a little bit deeper into this whole Arrhenius acid and base, Bronsted-Lowry acid and base. And believe it or not, there's actually a third categorization for acids and bases. But let's just explain this very quickly. And to do that, I'm going to get rid of myself and I'm going to bring this up. So we know that an Arrhenius acid and base is the most general definition, the oldest definition. It's one that looks at, are you increasing the, now don't pay attention to what's on the screen now, but are you increasing the I'm sorry, are you increasing the hydrogen ion concentration? If you are, then you are an Arrhenius acid. Are you increasing the hydroxide ion concentration? If you are, then you are an Arrhenius base. Easy, right? Does it completely disassociate? Does it partially disassociate? Let's take a look at Bronsted-Lowry acids and bases. And for that, take a look right down here on the little PowerPoint slide. We see that a Bronsted-Lowry acid and base, a Bronsted-Lowry acid is something that donates a proton. A Bronsted-Lowry base is something that accepts the proton. And this kind of makes sense. You can kind of think to yourself, well, you know, how am I going to remember that a proton is donated, it's an acid, a proton is accepted, it's a base? Well, think about it this way: protons plus charge, hydrogen ions are usually plus charges. So it kind of aligns, right? Arrhenius, you increase the hydrogen ion concentration, it's an acid. Well, Bronsted-Lowry, you're donating a proton, that's a plus, right? So it's an acid. And you would accept the proton and you're a base. So to better understand what this means in terms of a chemical reaction, take a look at the little chemical reaction right here. We see we have the bicarbonate ion, and we're adding that with water. In this case now, we are going to get carbonic acid with hydroxide. So the simple act of donating a hydrogen from water or a proton from water will make water our Bronsted-Lowry acid, and the carbonate ion, the bicarbonate, excuse me, our Bronsted-Lowry base. Okay, it accepts the proton. This one donates the proton. In this case, we have our bicarbonate and our hydroxide. When we combine those in a reaction, we get the carbonate ion and in water, we see that we are now donating a hydrogen from here. So in this case now, this is the Bronsted-Lowry acid. Before it was the base. So depending on your reaction, the same compound could be either a Bronsted-Lowry acid or a Bronsted-Lowry base. It all depends on whether you're donating a proton or accepting a proton. Okay. Here again, very simply looking at this, we have HCl and H2O. Well, we see HCl will donate its proton to H2O, giving the hydronium hydronium molecule H3O plus and a chloride anion by itself. So the HCl in this case is also a Bronsted-Lowry acid. The H2O in this case would be a Bronsted-Lowry base. It accepts it. And then we get these two things on the other hand. Notice up here, there's something called a conjugate acid-base pair. Well, if we look at a reaction as reactants and products, here we have our reactants, here we have our products. We see that HCl in this case would be the Bronsted-Lowry acid, and H2O would be the Bronsted-Lowry base. Well, as the reaction occurs, things change, and a hydrogen or a proton jumps from here to here, leaving now hydronium ion. Well, this hydronium ion could in turn donate its proton to the chlorine in order to form hydrochloric acid again. In that case, H3O plus would be the Bronsted-Lowry acid. The point I'm trying to make here is that as a reactant, H2O was a Bronsted-Lowry base, but now as a product, it's morphed into an acid. It is an acid base, or in this case, a base acid pair. It's a conjugate pair. The same thing with HCl. This was the Bronsted-Lowry acid. Now Cl could accept a proton and become a Bronsted-Lowry base. Again, acid-base pair. So what I'd like you to understand here, oh, here's another one. What I'd like you to understand here is that if something is an acid to begin with, it's going to have a conjugate base. If something is a base to begin with, it's going to have a conjugate acid. And those are the pairs. Here's another one. The acid that donates the H, so that means Br minus would be the conjugate base pair. Here's water, it accepts. That would mean that would be the conjugate acid. And remember, just because something is a Bronsted-Lowry base in one case, it could be a Bronsted-Lowry acid in another. If I was a really good teacher, I'd find that for you quick. But the old teacher let you down, so that's okay. Here's an example, kind of an example we looked at before. Acid here, conjugate base, it gives it up. Here's base here, conjugate acid would accept it and would give it up later. So conjugate acid base pairs, here's something that's a little bit more in depth, but something you guys can definitely handle. We see here that the this acid is donating, it's giving up the hydrogen, so that hydrogen will appear over here, and there it does. We increased H2 to H3. So this accepted the protons. It is now a conjugate acid, base to acid pair. Here the acid donated the hydrogen. Acid has now a conjugate base. All right, so hopefully that clears up some things about the Arrhenius acid and base definition, the Bronsted-Lowry acid and base definition, and the difference or the relationship between an acid and its conjugate base, or the base and its conjugate acid. I don't think your book gets too much into conjugate acid base pairs, but I would definitely suggest, hey, do a little research on it. Find some videos. There are plenty of videos out there that will enlighten you a little bit more. It's going to bring us to our next point here. And I don't believe your book gets too much into this, but there is yet a third definition for acids and bases. So we have the Arrhenius, you have the Bronsted-Lowry, and third, you have a Lewis acid and a base. And a Lewis acid and base is kind of like what this diagram is showing us right here. It has to do with Lewis structures and the movement of lone pairs of electrons. In this case, the lone pair of electron is going to want to move over and take this hydrogen away. Then this lone pair will jump onto the oxygen. In that case, it's now going to accept a lone pair. This is going to donate a lone pair. When we're donating a lone pair of electrons, we are talking about a base. When we're now accepting, so this little lone pair here, this bond, it's going to become a lone pair, and we're going to accept it onto the oxygen. That's going to become an acid. So we talked about Arrhenius and then Bronsted-Lowry. Well, Lewis acids and bases now encompass yet a larger set of compounds. Okay. Here's another good example of a Lewis acid and base. We see the lone pair here is being donated. That makes this the Lewis base. It's being accepted over here. That makes this the Lewis acid. Okay. Again, your book really doesn't get too much into this. Here's a nice little slide if you want to jot this down to keep everything straight. Arrhenius is H plus in water, OH in water. Bronsted-Lowry was a hydrogen donor. Bronsted-Lowry base was a hydrogen acceptor. Lewis acids accepts electron lone pairs, and Lewis bases donate electron lone pairs. Again, if you want to take a little bit more research on this or do a little more research, I definitely would compel you to do so. Your book really doesn't get into it too much, but it's definitely an interesting topic, a fun topic. So There again, we're just broadening our sense of what an acid and base is. So enough of that. Let's get back to the whoa, there I am. Let's get back to the PowerPoint. Let's make me small because we don't need to see that much of me. Good grief. All right, here we go. So all this talk about acids and bases, these acids and bases do need to react with one another. And when they do, we have an acid and base reaction. An acid and base reaction in the one above, we see water reacting with ammonia, okay, NH3. This produces the hydroxide ion and an ammonium ion, and we could see which one is the acid, which one is the base. In this case, it's not so much of increasing or decreasing, increasing the hydrogen ion concentration or increasing the hydroxide ion concentration. So we cannot categorize these as an Arrhenius acid and base. However, we can categorize them as a Bronsted-Lowry acid and base. And the reason we can do that is because we see that water donates a hydrogen ion or a proton, and ammonia would accept it. So in this case, water would be the Bronsted-Lowry acid, ammonia would be the Bronsted-Lowry base. See if you follow along, hydroxide here, because this is the Bronsted-Lowry acid. This is the conjugate base. Here we have the Bronsted-Lowry base. This is the conjugate acid. They're just pairing up. Reactions between acids and bases are called neutralization reactions. So remember from the past video, we talked about these replacement reactions or the metathys reactions. Now we have neutralization reactions. When we do bond an acid and a base, it's called a neutralization reaction because it neutralizes the acid and base. And when we have a metal hydroxide as a base, we get a salt or an ionic compound and water. And those are your very typical, when you say acid-base reactions, you're usually thinking an acid plus a base gives you a salt and a water. So those are usually our the Arrhenius types of acids and bases. Moving on, here is an acid and base. Products are generally a salt and a water. Here we have acetic acid, right? Choo-choo, right? So we have the acetate ion and sodium hydroxide. There's our metal hydroxide. We have sodium acetate along with water. This is our aqueous salt. Just because something is a salt doesn't mean it doesn't dissociate in water. In this case, it did. So we have our aqueous salt and our liquid water. Traditionally, the sodium would be written in front. Positive ions come first, followed by the acetate being the negative, the anion. Again, strong acid like HCl reacts with a strong base like sodium hydroxide. The net ionic equation is circled below, but see if you can remember from the previous video, here we have the what equation? The molecular equation. Here we have the what? Ionic equation. And down here circled, we have the net ionic equation. Do you remember what these are called when we cross these out? These are called what types of ions? I'm not going to do it. I'm not. Spectator ions. There you go. We're crossing out those spectator ions because they appear on both sides. All right. Let's keep moving. You guys are doing excellent. Very good. Very good. So gas forming reactions. So in a replacement reaction or metathys reaction, may not give the product expected. So when a carbonate or a bicarbonate reacts with an acid, it produces a salt and carbon dioxide and water. So again, we see here is our acid followed with our conjugate base over here, the water. And here is our calcium carbonate. Here's our calcium chloride aqueous and our CO2, which could then receive, so that would be our conjugate base, conjugate acid, conjugate base, base, conjugate acid. And don't take me to the bank on that one. But in turn, we do have an acid and a base that would form a salt and a water, but it also releases carbon dioxide. So we have this bubbling effect. Same thing here, sodium bicarbonate reacting with hydrobromic acid gives us sodium bromide, water, and our gaseous CO2. This reaction gives the predicted product, but you have to carry this out in a hood because it does produce hydrogen sulfide. So sodium sulfide, when reacted with sulfuric acid, produces sodium sulfate plus hydrogen sulfide gas. I apologize. It has been a long day, folks, but let's keep on pressing because I know you guys are doing the same. So keep that chin up, not too far up, and keep going. You guys are doing great. So I told you we're going to break this into two sections. So I got one more slide for you on this one. Similarly, when a sulfate reacts with an acid, it produces a salt, sulfur dioxide, and water. Here again, strontium sulfate reacting, strontium sulfite reacting with hydroiodic acid gives us strontium iodide plus sulfur dioxide and water. So we're going to end this one here. We're going to pick up with oxidation reduction reactions, and hopefully we're going to finish the PowerPoint with this next and final PowerPoint or video. Guys, it's been wonderful. I look forward to seeing you guys in the next. Stay safe. Remember, chemistry is life. And have a great day. All right. Bye, everybody.